Okay, complex numbers. What are they?
Still don't know.
Okay, can you give me an example of what a complex number is not?
Zero.
You're correct. 0 is not a complex number. Somebody said 1. 1 is not a complex number.
I feel like an irrational number would be complex.
Question mark. Good. An irrational number actually is not complex. Even though like the word complex in English, it's kind of like complicated, and we think that like pi is complicated because it never repeats and it never ends. Irrational numbers are actually not complex numbers. But that's probably the best guess that I'm going to get. So I'm just going to go ahead and remind you what a complex number is. Does this ring a bell? Okay, imaginary numbers. Now, imaginary does not mean that you can't see it, nor does it mean that it doesn't exist. What is the definition of an imaginary number? So if, we use I to denote an imaginary number, what is its definition?
I have an acronym for it.
For what? There's just one number. What is there an acronym for? There's just one number that I is equal to by definition.
The square root of negative.
Thank you, Sebastian. The square root of -1. That's it. So imaginary numbers, don't mean that they're not there, or that they are they can't be seen or they can't be drawn, because if you notice, the title of the section is called the complex plane, and we graph things on planes. So in a little bit, we're actually going to be graphing complex numbers. So by definition, what they allow us to do is they allow us to take the square root of negative numbers. Okay, so a complex rectangular number has the form a plus bi. And if you think back to what we've been talking about the last couple of days, a rectangular number on the rectangular coordinate plane, like a coordinate point, would just be like x comma y, versus polar, which has r comma theta. So a complex rectangular number is going to be considered a plus bi. Now, y'all remember when we did the quadratic formula, and we like if you get x equals negative b plus or minus square root of b squared minus 4ac all over 2a. What part of this is your discriminant? Okay, stuff under the square root. If your discriminant was negative, what kind of answers did that give us? Imaginary. And the whole point was because that's, you have a negative under the radical. So what happened was when you actually, let's say we ended up with like -2 plus or minus square root of 9i, or no, it'd be square root of -9, and you wrote your answer, you would get like, okay, -2 plus or minus 3i. And you don't need to write this, by the way. Just follow along to where one of your roots was -2 plus 3i, and the other was -2 minus 3i. These are called conjugates of each other. So those roots were the same numbers with the opposite sign in between them. So that's kind of where you have seen the rectangular form of complex numbers before, is in your answers to quadratic equations. Now, a rectangular number in the complex realm has a real part. So a is a real number, so that's the real part. And then bi, obviously, because it's got the imaginary number, is the imaginary part. Side note, if you don't typically write your i's with a little tail on the bottom, I recommend you do so, because if you write like 9i like this, and maybe your dot is really small, it might be really difficult for me to not mistake that for a 91 or something like that. So mathematically speaking, in a textbook, or when people are doing proofs, they always write i's like this. Okay, so the types of problems that you're going to see are like this number 1 here. It says solve the equation where x and y are real numbers. And I'm going to give you the equation. 2x plus y plus 3i equals 9 plus xi minus yi. Lots of variables, lots of i's. So as we solve this, out to the right, I'm going to scribe what we're doing on each step as we do it. That way when you look back at this, you know how we simplified from one step to the other. So the idea is if I want to solve, I'm trying to get, I'm trying to figure out what x and y have to equal in order for this to be true. Well, what you want to do first is you want to group your real numbers versus your imaginary numbers. Now, sometimes that grouping might literally mean rearrange, and or sometimes it just means like use parentheses so that you kind of understand the separation of them. Okay, so what I want to do is I'm going to do my real numbers in red. So on the left side, I'm not really going to do anything different. I'm just going to put parentheses around 2x plus y. And then I'm going to do my real numbers in blue. Sorry, opposite. The imaginary numbers in blue. So I didn't change anything. I just grouped my real numbers with parentheses around them. And then on the right-hand side, you have a couple different options. The only real number you have is 9. For the imaginary number, at this point, you could, if you notice they both have xi minus yi, if you wanted, you could factor out an I, or you could just leave them as is for now, but put parentheses around them, xi minus yi. And then after you group them, so this one wasn't really strenuous in terms of having to group them other than putting parentheses. And even then, y'all are probably you could have put parentheses on like the original equation. After you group them, then you set corresponding parts equal. Set corresponding parts equal. In other words, you're going to set the real parts equal to one another and the imaginary parts equal to one another. So if I set the real parts equal, then I get 2x plus y equals 9. If I set the imaginary parts equal, I get 3i equals xi minus yi. Now, if I'm going to solve, if I'm going to figure out what variables x and y need to equal, I need to try to simplify these equations as much as possible before proceeding. So in doing so, I can go ahead and get rid of the imaginary component in the blue equation. If I divide every single term by I, then I cancels from all three of those numbers. And it just leaves us with 3 equals x minus y. Okay, once you get down to these two equations, then this question becomes very algebraic. Then all we do is solve the system of equations. Using, there are a few different things you can do. I would say the most common methods would be elimination, substitution, etc. So you'll take your two ending equations, 2x plus y equals 9, 3 equals x minus y, and then you want to go ahead and solve those. Some people just prefer substitution. I think if you look at these two equations and you notice that one has a positive y and one has a negative y, to me it just makes sense to line them up and eliminate. Because if you line them up and you add them together, then y minus y cancels. And then you get 2x plus x, which is 3x, equals 9 plus 3 is 12. And then if we divide both sides by 3, then we get x is equal to 4. And then to figure out what y is, all we have to do is plug 4 back into either one of these other equations. And in doing so, we would get that y is equal to 1. Does anyone have any questions about any part of that? Can you be verbal with a yes or a no? I'm going to assume you said no. I have a feeling the mic on y'all's end is actually giving trouble. Okay. Oh, I heard a little bit of something there. All right. Here's the next bit. As I mentioned earlier, we're actually going to be graphing imaginary numbers. In doing so, they're going to be graphed on what is called the complex plane. So you've graphed rectangular coordinates on a rectangular plane. You've graphed polar coordinates on a polar plane. A complex plane could be either rectangular or polar, but the main difference is that the horizontal axis is not going to be an x-axis anymore. It's going to be the real axis, and the vertical axis is going to be imaginary. Show of hands, how many of you are in the habit of putting an x and a y alongside of your axes every time you graph an equation, or every time you graph anything? Yeah, okay. So in this case, usually I'm fine. I'm not too picky about whether or not you label your axis, but on the complex plane, you have to. You have to do it. You have to show me that your horizontal axis is the real numbers and your vertical axis represents imaginary numbers. Okay, so basically they will take on the form. If I earlier said that it was A plus BI, they will take on the form. They're actually really easy to graph. Because what will occur is you start at the origin, you go along. A, as we said earlier, was kind of like, A will almost kind of like act as the x coordinate. But since A is the real component, you'll start at the origin, you'll move along the real axis for A, and then you'll move along the imaginary axis up or down for B. So A plus BI would be essentially the hypotenuse of the triangle. Does that make sense? All right. Next up. The next type of questions. Well, the absolute value of a complex number is exactly what it sounds like. Typically, when we dealt with vectors, we refer to this as magnitude. When we're dealing with complex numbers in the rectangular plane, this is being referred to as absolute value. And it's exactly what it sounds like. If I tell you, so if I give you a complex number z, and I'll tell you that it's a plus bi, then this implies that the absolute value of z is going to be the square root of a squared plus b squared. By definition, can you tell me what absolute value is? By definition, what is the absolute value of something? Is somebody trying to say something and I just can't hear you? Yeah, good. Okay, so if it's just the distance from 0, then another way to think about this is it would be the magnitude of the vector if the hypotenuse were considered the vector. The deal is distance is always positive. So anytime you find, if I ask you for the absolute value of something, your answer is always going to be positive. Okay, so the types of questions you're going to see are if I ask you to graph the number and then find its absolute value. So we'll do a couple of these. Example A. If I tell you that z is equal to -3 plus 2i, I want you to graph this number and then find its absolute value. So remember, when you draw a graph, you must label the horizontal axis as real, vertical as imaginary. So graphing is super, super simple. If you start at the origin and the real part is -3, so we're going to move to the left along the real axis. Imaginary part's +2, you're going to move up 2. So then this, and you actually graph the segment that represents the number, not just the point. Okay, to find the absolute value of z will be the square root of a squared plus b squared. So that's going to be the square root of 3 squared plus 2 squared. Which is going to be the square root of 3 squared, -3 squared is 9 plus 4, which is 13. By now in your math career, you should know, unless I specify to round to the nearest hundredth or something, always leave radicals in simplest radical form, though there are no square numbers that are factors of 13. Let's do another one like this. Another complex number z, this time, is going to equal -4i. So where would this number be? Since there's no real component, yeah, we don't go left or right. Just go down 4 on the imaginary axis. Find the absolute value. Now, you actually don't have to compute the absolute value. If absolute value means the distance from 0, how far away is the end of this from 0? Yeah, you can just count the lengths, or count the units, I'll say. Otherwise, if you miss out on that, your real component is going to be 0 squared plus -4 squared. Actually, I don't even need to do that. When you take the square root of 16, you're just going to get 4. Okay. Questions so far? Okay. Now, I'm going to erase some of this. Regular. Let's title this next section Regular to and from Polar. So this is just going to recap all of our equations that we did in section 9.3 about how we go from rectangular to and from polar coordinates. So first of all, we need to remember that rectangular coordinates have the form x, y. Polar coordinates have the form r theta. And there are 5 equations that we can use to go back and forth from each one. So I think the 2 easiest equations that people tend to remember are what x and y equal. X is equal to r cosine theta. Y is equal to r sine theta. And then r and theta in your polar coordinates, r is going to be square root of x squared y squared. And then theta has 2 options. Theta is either going to be tangent inverse of y over x, or theta is going to be tangent inverse of y over x plus pi. How do you know which equation for tangent needs to be used? Did anybody say anything, or is the mic that bad now? Why do I hear y'all the second time? That's so strange. Okay, I'm just gonna go ahead and assume that y'all said what I needed you to say. Oh, no, okay, so that time nobody did really say anything. All right, think about it. Or look at your notes if you have to.
Oh, you use the one where you add pi when x is less than 0.
Very good. So you use you just do regular arctangent when x is greater than 0, and you add the pi when x is less than 0. P.S. You need to know these for your test. They're not going to be given to you. So I think many of you know the x and the y ones, and you probably know r at this time as well. But I could see theta giving you guys some trouble if you're not careful to study those. Okay. If I want to do a little manipulation here. If I give you a rectangular number, a plus bi, and again, that is a number in the rectangular form, then can we substitute in, so using some of these equations that we just talked about, if we know that like a is essentially the same thing as x and b is essentially the same thing as y, if we substitute in these values for that, then instead of a plus bi, we can rewrite that as r cosine theta plus r sine theta, which implies that our complex polar numbers, so earlier we talked about the rectangular, this is the rectangular number. Polar numbers are going to be written in this form. I'm just going to rearrange it a little bit. Most times we will see the r being factored out, cosine theta plus, oh wait, I forgot the I over here on r sine theta I, because that's bi. So r times cosine theta plus I sine theta. This is a complex polar number. Or sometimes you may see this written as, there's like an abbreviation for this, which is going to be r cis theta. And it's just a shorthand way of writing cosine plus I sine theta, but you could write it like this instead. Now, r and theta have, I don't want to say different meanings, but we call them different things in the complex plane. So in the complex plane, r, which is the length of our hypotenuse, is the modulus. R is what we call the modulus. And theta is, yes, it's kind of an angle, but it's also referred to as the amplitude of the triangle, which makes sense, because it's basically where your acute angle is opening up to. So it's your amplitude. Okay, so types of questions that you're going to have that deal with this is if I ask you to express the complex number in the polar form. So your whole homework was essentially going back and forth between polar and rectangular. So this is going to be very, very similar to that. So first example, A, we'll do -3 plus 4i. I want you to express this in polar form, and if necessary, we're going to round our answer. Okay, in polar form, this is what polar form looks like. So in polar form, we need r and theta. Need r and theta. Well, I give you the rectangular form, -3 plus 4i, which is where x would be about -3, and then y would be 4. So if I use the same equations that you did in your homework to convert from one to the other, then we can solve for r and theta, and then plug that into the complex, plug that into the actual complex form. So if we know r is the square root of x squared plus y squared, then we can substitute in, that'll be the square root of -3 squared plus 4 squared, which will be 9 plus 16, which is 25, and the square root of 25 is 5. So r is equal to 5. Okay, in order to find theta, we're going to use one of our inverse tangent equations. Now, before you pick one, remember what we said a second ago, they both rely on x. So since, if you look in the rectangular portion, we've already talked about that x was -3. So since x is less than 0, then we're going to use the equation theta is tangent inverse y over x plus pi. So then we substitute in our values. Tangent inverse of y over x is going to be 4 over -3 plus pi. Now, in the beginning, I told you that you were allowed to round. So with that being said, when you get to this point, you can go ahead and plug this into your calculator as is and then round it. Typically, in here, we'll round to the nearest hundredth. You've got to be sure that your calculator is in radian mode. Most of this chapter, unless you're given a problem that explicitly has degrees in it, our default mode needs to be radian. So you got to make sure you're in radian mode before you type that in your calculator. So when you do that, you're going to get that theta is approximately 2.21. So once you find r and theta, then you plug in these numbers into your complex polar number template, so to speak. So again, you can write that in two ways. You can write 5 times cosine of theta is 2.21 plus I sine theta is again 2.21. Or you can write it quickly as 5 CIS 2.21. I see many of you wanting to abbreviate that each time, which isn't an issue, but I'll say like tomorrow when we go backwards from what we're doing right now, you'll see it as the elongated version of it, but I'm okay if you use the abbreviation that I've shown you here. Okay, let's do one more like this. Example B. The number 1 plus square root of 3i. This time I want your answer to be exact. So no rounding. Same question. I want this in polar complex form. So I need r and I need theta. So r will be the square root of x squared plus y squared. So it'll be the square root of 1 squared plus the square root of 3 squared, which will be equal to the square root of 1. What is the square root of 3 squared?
3.
Just 3. And that'll be square root of 4, which is 2. So there's one. That's the easy part. R is 2. Finding theta is a little bit more lengthy than this one. This time, your x term is positive. So since x is greater than 0, then theta is going to be tangent inverse of y over x. We don't need to add pi. So then we get theta is equal to tangent inverse of y is square root of 3 over 1. Because I asked you for the exact value, you cannot just type this in your calculator and give me that answer, because that's going to give you a decimal. Instead, you think about what this is asking. This is asking what value of theta do I have a tangent value of square root of 3? Or if you need to see it a little bit differently, if we take the tangent of both sides, then it cancels out tangent inverse on the right side. And then we have tangent theta equals square root of 3 over 1 is just square root of 3. What is tangent? How do you find tangent? Or like logistically speaking, what is tangent? Slope, right? And we find slope by rise over run, or in this case, y over x. So your knowledge of the unit circle, and Tyler, we talked about this a second ago, it needs to expand beyond just the x and the y coordinates, and you also need to become equally as understanding of the slope at each one of these angles. Let me draw this one a little bit better. So I want to go through and I want to do the slope of these 5 angles that span quadrant 1. Because you need to know these just as much as you need to know the actual coordinates for this chapter. So what is the tangent of, I think I'll typically like dealing with degrees better. Well, no, I'll write it as radians. What is the tangent of 0? What is the slope at 0? Did anyone say an answer? 0.
What? 0.
Thank you. Okay, what is the tangent of this 90 degree is the same thing as pi over 2. What is the tangent of pi over 2? Okay. The middle one is the tangent of pi over 4, the same thing as 45 degrees. That one should be another easy one.
1.
Good, because the slope is y over x, both those are the same thing. The other ones are a little bit different. This tangent of, this is 30 degrees, it's the same thing as pi over 6, and then at 60 degrees, it's going to be pi over 3. And those are a little bit more challenging to figure out. On my video tomorrow, I'm going to explain how you find these. Right now, I just want you to trust me for the sake of time. The tangent of pi over 6 is the square root of 3 over 3 when you divide its y coordinate by its x coordinates. And then when those flip for tangent of pi over 3, that one's going to just equal the square root of 3. So if you use this information, then tangent of pi over 3 is equal to square root of 3 answers our question. Then we're able to get that, okay, theta must then equal pi over 3. So then as your answer in complex polar form, you can write it as 2 cosine pi over 3 plus I sine pi over 3. Or you could just write RCIS pi over 3. Okay, last type of questions. I want you, what number am I on? Did I keep number things? All right, so this would be number 4. I want you to graph the following number and then express it in rectangular form. So I want you to graph the number 4 times the cosine of 11 pi over 6 plus I times the sine of 11 pi over 6. Then express it in rectangular form. So it is given to us in a polar form. Rectangular form should be in the form of A plus BI. Okay, so to graph this number, let's do that part first. What variables do these numbers stand for? What does 4 stand for?
R.
R. What does 11 pi over 6 stand for? Theta. Now, you don't have to draw the entire polar plane because that would be a little bit complicated. But, you know, if you just kind of, I don't even want to draw a circle. I guess I will. Okay. So if we draw a couple circles, R is going to be 4, which means we need at least 4. Oh, this is going to be beautiful. Oh, no. Oh, no. Oh, no. All right, that's the best I can do without putting my hand on the screen. Okay, if I graph this point, so this is a recap of section 9.1. If I want to graph the point 4 comma 11 pi over 6, you typically want to locate your angle first. Where is 11 pi over 6? Or what degree is that equivalent to? Because I know y'all are more confident in degrees. Okay, so it's 330. Because it's down negative 30 degrees. So then it'll be along this vector and then outward 4. Okay, I guess I can erase the vector parts because it's just going to be that. Okay, then express it in rectangular form. Rectangular form is a plus bi. This part is actually extremely simple because in order to do that, all you do is actually simplify the polar form. What I mean by that is, let's leave 4 alone for now. If you look at the unit circle, what are the coordinate points at 11 pi over 6? Like, what are the x and y coordinate points there?
3 over 2, -1/2.
Very good. So then if I substitute in those values, we know cosine is the x coordinates. So that's just going to be -1/2. And we know, so this will be plus I. We know sine is the y coordinates, which is square root of 3 over 2. Whoa, 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 whoa. You big dummy. Yeah, sorry. It's been a long day. All right, let me try that again. Cosine is the x coordinate, which is square root of 3 over 2, plus I times sine, which is the y coordinate, will be -1/2. And then your goal is just to simplify these things. Well, the 4 is going to distribute to both of those, right? Well, you can't add, I is kind of like a variable. So even though it's a complex or imaginary number, you can't add it to something that doesn't also have I. So then you'll get 4 square root of 3 over 2 plus -4i over 2. And then both of these are divisible by 2, so you can reduce it one more time. 4 over 2 is 2, so you get 2 square root of 3 minus 4 over 2 is 2i. And this now has the form a plus bi like we wanted, so that part would be your final answer. Any questions about that?